Let us start like that. So I have started the recording. Okay, let's share my screen. Okay, so now I am sharing screen. I hope you can see this. And okay, so this is where we are. Almost we are close to the finishing. So today we'll mainly discuss the assignment 9 and whatever doubts you have in that Hartifork and as well as in VBT if you have look at the videos, whatever the videos you have touched upon till now. And I will share some of the tutorial problems like before after this session. So I'll share in the discussion forum. So I think that is about that what is the angle, how to get the angles and that other things. Some tutorial problem which will be solving next week. That is maybe on. So you yeah, that will be solving next week. So we'll try to finish in such a way. Suppose your week 12. Let me give you a spoiler that in week 12 there will be only three videos, only three lectures will be there. So you will try to watch that with week 11 only, so that we can discuss it at maybe on. See, this is week 10 live session, so that we can finish by week 12. So we'll try to do something like that because only we have only three lecture videos on week 12, which based on which only two are lecture slides and one is the summary thing what professor has made. So let us start today's lecture, today's session, and let us first start with the assignment 9. So what do you think? So let us start. Do you have any specific query here, week 9, or we can just go one by one, and if some query is there, we can discuss there, right? So
Yeah, that would be great.
okay. So in atomic units, the mass of unit of mass is the mass of a electron, right?
Electron, yeah.
Yeah. So that is discussed in the lecture video itself. So that 9.11 into 10 to the minus 31 that we are using as a one atomic unit. So now in atomic units, the angular momentum L is equal to 4. And that is we have already solved, right? That is, I
Yeah, root
guess,
20.
yes, L into L plus 1. And in atomic unit, so this we don't have to think. This is in atomic unit, right?
Yeah.
Momentum is H cross is the unit in atomic units, right? Of momentum. Okay, so you can solve it. I think come as root 20, right?
Yeah.
Maybe, and I don't remember the exact thing. 4 point something because it will be in between the 4 and 5. Okay, and this is I think it is given, right. 130 is two times, right?
Yeah.
Two times. Then what is the next question? The unperturbed Hamiltonian for helium atom in atomic units. Okay. So that Me, then other H cross, these things will not be there. So what will be the answer? Can anyone tell me and why it will be that such that?
B,
B.
because in other cases the signs are not same.
Okay. So this is the kinetic energy term, right? For first one, this is the second one. This is the potential energy for attraction,
Attraction and repulsion.
and this is for the yes for the second electron. Yes. So here we are, as it is written unperturbed. That's why we are not dealing with that
Repulsion.
repulsion term. Yes. So that's why this term is already gone, right? A is cut, B is the right answer as you have seen, and these things as you have told. And why this is minus? The sign of this minus because this is attractive potential energy, right?
Yeah.
Yes, yes. So B is the right answer. What is the next slide? Okay. So this is I have discussed with the NPTEL member. So as per you are correct, the trial wave function was not given, that is cos lambda x, right? Something like that, and there will be some this parameter has some range lambda x. So that is not given here. So what we have thought that will give number to everyone. for this question. So this is being done with, and we have seen this answer will be 1.14, right?
Yeah,
From the
Yeah.
lecture series.
from the last
So
assignment.
yeah, we have also done in the last assignment. Yeah. So in both the assignment, not in the both, not both both the cases. For these cases, we will give marks to the everyone. Okay. So now for question number 6, for helium atom, a good variational parameter would be. So what
Nuclear
would be the good variational parameter?
nuclear charge.
Nuclear chain, right? Yes. So, and as
Nuclear
you
charge.
can see, this round shaped option means only one option is correct. So, if you are getting on your answer, so there means not multiple question right answers are there. And this is, I think, also discussed in the lecture video, right?
Yeah.
Yeah, it was directly mentioned.
Hmm.
Yes. Actually, some artifact problem will be there in week 10, I guess, right? I guess in week 10 assignment, there are some more Hartree-Fock problems are there. Koopman's theorem, maybe something like that. I have to
Yes,
check.
in like 2, 3, like the earlier, the
Yes, yes,
the questions from the beginning, they are from this week.
yes, yes. So it was prepared in such a way that earlier some TA, whoever was the TA, they prepared it something like that. So I also didn't pay much attention to the next week question, but later I find out that okay, some problems from this week's lecture are also there. So it could have been um, sent to in this week's lecture itself, but I have done in some other weeks assignments in such way. So we'll deal with them in the next week. So let us do the question number 7. Let the functional e of phi. So these have been taught, right, that e of phi is the functional.
Hmm.
These have been mentioned. So this is given as z square minus 7z for barium, beryllium,
Beryllium.
beryllium. So z is 4 for this, right?
Hmm.
Z is 4. Now we have to calculate the shielding constant. And from variation theorem, we know that if we got the average energy, that is z square minus 7z, then we need to check that for which value of this z is our parameter here, variational parameter. So we have to check that for which value of z, this is e of phi is
Zero.
minimum. Yeah, e of phi is minimum. That is the derivative is 0.
It should be zero.
Yes, so that is 2z minus 7, and that will be 0 for this minimum e of phi
Yeah.
functional. So you will see that z will be
Z
3.5.
effective.
Yes, z effective.
Hmm.
Right. This is z effective because this is the minimum. Yes. So now, so what will be the shielding constant? Shielding constant will be z minus z effective.
0.5.
That is, I think, 0.5. Yes. Okay. So I think you guys got this question, right? Both of 0.5. Okay. And now, 8 and 9. In Slater type of orbitals, in order to get the variational parameter, the scaling is performed on. So now the Slater type of orbitals, we have already seen that this is almost kind of this 1s orbitals, uh, where the uh, R polynomial was missing. Else everything
Yeah.
was there, right? That spherical harmonics is there. This was missing only. Everything was there. And based on that, what we have said that this radial wave function we cannot. So in both the question we are dealing with the Slater orbitals. So let us first see the first question. So in Slater type of orbitals, in order to get variational parameter, the scaling is performed on. So the scaling is performed on the atomic number, right? The Z
Hmm.
and N, right?
L.
N is the
Hmm.
principal quantum. So that is both of them are there. So we don't really care about the azimuthal quantum number, that is L. That we don't really and atomic mass that is not a variational parameter. So these two are the variational parameter that we use as a variational parameters. Okay. So for question number 9, the question is the Slater type orbitals have mutually orthogonal radial paths. Is it correct?
No.
No,
No,
there
right?
is no radial part.
Yeah, so there is no orthogonal radial part because the radial what is the polynomial is missing.
Yeah,
So
in
they
R.
don't really have the radial nodes also, right? But they have this periodical harmony. For that, they can have angular nodes, right?
Yeah.
And they can form a complete set. Yes. So these two are the right answer, the C and D. And the first two are will not be the correct answer. So that's all for this assignment. Now you tell me if you have any um, particular problem or from this Hartifop lecture series, because it was really tough. So we'll try to see the videos and we'll try to discuss that thing. And before that, let me tell you, in previous week we were discussing about that Hermitian operator thing, right? That to for this F star A G, that will be equals to uh, d tau tau, that will be equals to G
Star. Oh
uh,
no, sorry. G A F.
F something like that, right?
Yeah.
So this will be done only when this A is a Hermitian operator. Means we are taking that A as a Hermitian operator, and we are our main doubt is that if psi that is equals to C1 F plus C2 G, if psi is a uh, operator or a eigenfunction of A or not. So I tried to see Levine. So they did not mention that particularly Levine, or yeah, I think I have seen the thing from Levine. So they also didn't mention it directly that psi is a eigenfunction, but it should be, because they said that similarly what argument Sir has used, that started from F and G, that when A is working on F, that is giving A of F, and for G also A is working on G. So they didn't mention that this is A, but they just said that G is a eigenfunction of A. That way, they have written that we can also think that if, with similar argument, they have started from these, right? Psi A, psi, or you can say this like this bracket notation, that no, from this bracket notation it will not be evident, right, what we are trying to say. So psi star A psi d tau, that is psi A psi. So so this right hand side is equal to left hand side they have written. So it must be psi should be a eigenfunction of Hermitian operator A. So, and whatever things Avinash has showed at the end as a PowerPoint presentation, that was also correct. Correct means that was the rest of the calculation what was not mentioned in the lecture series, right? What we are
Yeah.
discussing at the last moment.
Yeah. The calculations were all perfect. I
Yes, yes.
also got exactly the same calculation.
Yeah. So Avinash was also correct in that part. But I think psi will be an eigenfunction. That's where we can write this particular thing, this thing. That, and from there we are going to get this f star a hat g d tau is equal to integration of g sorry, the operator hat will, operator sign will not be there on g acha, I have given it twice, so that was a mistake. G A hat F whole star. Yes. So that was the thing we were discussing yesterday. I think two problem were there, right? One regarding this and one regarding that assignment problem. And another problem was there that I also talked, also asked to change that in NPTEL guide, that trial wave function, right? What Avinash was saying, that e to the power lambda x itself, the trial wave function, it was not a acceptable wave function. That so that we change this answer to e to the power minus lambda x square, which is a Gaussian type of wave function, trial wave function, and we have given marks to all. Means we are re-evaluating the assignment, and marks will be given to all whoever has attempted, or even whoever has not attempted also. This the marks will be given to all. Okay. So regarding that, when the notification will come, I will share. So now let us discuss if there is any doubt from the lecture series.
Regarding reevaluation, there was
Yes.
one question uh, in week six. There was a question where for an electron atom, there was like a wrong option was also given as correct answer in the multiple choice question. That
Acha,
hasn't been reevaluated.
Which
acha,
one?
let me go to the
Wait,
then
let
week
me check.
six one.
Yeah. Week six, question four.
Acha, week six assignment, right? So it will
Yeah,
be
yeah.
week seven. Question number seven.
Four.
Question
Week
number four.
six, question four.
Okay, so this one, right? For a n electron atom, acha, this term you said, na, that
Yeah.
the kinetic term of the Hamiltonian is a sum of kinetic energy terms of n one electron Hamiltonian. So the problem was that what was the exact problem for n? So let us solve this question again. For an n electron atom, Hamiltonian is a sum of n one electron Hamiltonian. This is not correct. Kinetic energy term is a Hamiltonian is a sum of in one electron Hamiltonians and 2s 2p are degenerate. No, electron repulsion is the why the Schrodinger equation is not separable, right? This was also, I think, correct option. So you had a problem with these things. So can you repeat the problem? What you
Yeah,
exactly?
like for an n electron atom, we were writing there was a kinetic term for nucleus.
Yes,
Then there was the kinetic term for electrons.
Mm-hmm.
yes.
So in the question, what they were saying for an n electron atom, so the kinetic term of the Hamiltonian is a sum of kinetic energy terms of n one electron Hamiltonians. It doesn't mention the nucleus term.
Yes, yes.
But according to this Born Oppenheimer approximation that we are doing right now, anyway, the nucleus kinetic energy will be always taken as zero.
Because
They
that
don't
is
move as fast as the
simul.
electron.
Yes.
But nothing is mentioned, right? In the
So
most general form should have the nucleus term.
Yeah, but I think wherever we solved it by anyway. We are calculating the energy of the electron part. So
hmm,
Hamiltonian is always set up for the electron.
Yeah, but in the question is asking about for the whole atom, right? For an electron atom.
still, yeah, Runatpan, when we are currently at doing this Hartree-Fock problem or multi-electronic system, see the last problem also for a unperturbed Hamiltonian which we solved just now. Let us go to that
Yeah, that also didn't have the nuclear part.
that this question, right?
Yeah,
You also didn't bother about the nuclear part. See, we have written helium atom itself, right? So I think in the lecture series also, I think your concern is correct. We have discussed this, I remember. Then I think I have talked to professor. That's why maybe we didn't do the re-evaluation then. I forgot that part. I don't really exactly remember. But the thing might be like that. What Avinash has said that due to this Oppenheimer approximation, I think this is also mentioned in the lecture videos also. So we have to take that whatever the kinetic energy term from the nucleus that has to taken as zero. Uh, for this kind of calculation. The problem you are saying that is also correct. Maybe we had to mention there that you can, or maybe according to Born Oppenheimer approximation, that part can be added. So that I will again discuss with. professor, and I'll come back. So for a
Okay.
general thing from now on, just ignore this nucleus term, the kinetic energy for the nucleus for the time being. Why
Yeah,
if
like
the
I mean,
atoms?
in this week's assignment, like we had the options where we can understand that yeah, we always we are
Yes,
ignoring the nucleus. But in
yes,
that week, in the lecture series, the most general form was also explained. So that's
yes,
why I was confused.
yes.
Okay.
No conditions was also written in the question that.
Yeah.
Yes, I understand. I understand. Yes. So that is one thing, and we can go to the lecture videos if I have, and then we can go to particular uh, slide by slide. Let me check. Let me unshare.
In the lecture series, the while
Yes.
teaching, it starts with the nuclear part, and the professor says that somewhere that yeah, this we'll ignore this part and we'll take only this.
Hmm. So let us see about
Yeah, but
perturbation
what
theory.
Arunarpal is saying is also correct, because if you over there in that lecture, it was said that since we are doing for electron, we'll ignore the nuclear part, and the question says for an atom.
Yeah, in the lecture, I think now that you mentioned, I also remember like we specifically said that we are writing Hamiltonian for
For
electrons
electron,
only,
yes,
Electronic
and
part, yes.
then we
yes,
change the equation.
yeah, yeah.
Hmm.
So
Because
you have
no, due to Born-Oppenheimer approximation, we actually separate the variables there. That nuclear part is different, and means nuclear part is nuclear motion is we can separate nuclear motion and the electronic motion. So, acha, you can't see my screen, right? So let me share my screen. We can go slide by slide so that if you have any problem, uh,
your screen. Yeah,
yeah, I think this is where the week 9 has started. Uh, so recapitulation of many electron atoms that has been
can
done.
you just go back one back?
Yes.
No, you are I think going back in the opposite direction.
Here.
Here.
Yes.
That top line.
Yes, that Hamiltonian is mentioned. That the nuclear
Yeah,
part is there. Yes.
yeah.
Yeah, it is the most general Hamiltonian. Then we are
Yes, it
writing
is.
electrons. So that's
Electrons
why
and
we were
upon
specifically
ignoring
writing
the
He.
yes, yes. Specifically written the He. So that is not for the
Hmm.
atom. That is
Hmm.
for a electron. Yes.
Yeah.
Okay. Then we are discussing that. So right now, what I am trying to do that I am trying to change. So that part I will take care. And now what I am trying to do that I will change the slides for the week 9, whatever has been taught in these classes. And if you have any specific doubt at any slides, then
Actually, to
please
be honest, week 9, I didn't understand enough
much,
to
right?
ask questions also.
So
Yeah,
I will
like
also yes, Arunatwa?
It was
yeah, man.
very
I mean,
abstract.
I had that problem like in week 9. My problem was I understood the ideas that Sir was telling us about,
Hmm.
but I couldn't feel like I can do something myself. Like
Yeah.
if we can do any
Whatever
programs
professor
or
was
any
talking, I
problem.
could understand that part,
Hmm.
but I really could not connect it elsewhere, anywhere else.
And
Hmm.
also, like I tried to find problems in books, and Hearty Folk is not mentioned at all in Griffith's book. And in
Okay.
Levine's book, there are so many problems in that chapter. Like I
Hmm.
couldn't even figure out which problems to do.
Okay. So I am also at your level only. I also understood what the ideas mainly, and whatever sir has generally taught, that is the part I also understood. But uh, in depth, maybe we have to read multiple times from the textbook itself, not from the lectures. What I guess, because I can see that we will get only the idea or the gist of the idea from this video. but I think we have to go to the textbooks and read thoroughly. So Hartree-Fock is just only the beginning of that. What can you say? The computational thing. Uh, so it's just a beginning. Uh, Maybe what Sir has told, that if he got another chance to teach the advanced thing, then might be when this recapitulation will be done or some more problems will be solved, then might be uh, it is clear. But I don't know when that course will be available in NPTEL. But I suggest you that you can read the textbook. Maybe I think did he suggest it? Pillars book and I guess some other books for this.
Sir, like in some cases, sir suggested specifically that the discussion was based on Macquarie's book, and
Macquarie.
in
Yes,
some cases he also mentioned that this is done in this way in Pillar, like that.
Pillars book. The notations are better in Pillars book, something like that. So my suggestion will be that if you are so for this purpose, I should not say this. But whatever the you can take the ideas from these lecture series, because Hartree-Fock is discussed only for 1 week and 6 lectures, and I don't think from only 6 lectures we can and for 30 minutes we can get a lot of idea. Uh, we should means the idea is clear, but we have to solve some numerical problems ourselves. But let us see what we can do. But let us go slide by slide. If any particular thing come up, then we can discuss, right?
Yeah,
Okay. So it has been started with that recapitulation of many electron atoms like that and effective nuclear charge. And if we can get the thing from variational parameters, the what is the shielding constant or not. So this is just a introduction that for atomic units. And now he has shown that how using different order of perturbation theory means to the energy correction, different orders of perturbation energy correction, how can we get to the experimental value. And he has shown that some paper was published or some studies has shown that 13 order perturbation can lead us to that, but not the change was not much from the first order perturbation, right? Using the first order perturbation, we went to 2.75, and then we are going slowly, means some point by point. Okay, and he also said that we should also look for the ionization energy also. So the and ionization energy for helium plus was found to be a two atomic units, right? Minus two. It came from simple
two, two hydrogen.
simple means Z is yes, two hydrogen orbitals, right?
Hmm.
Yes, it was like that. Now for this slide, he has discussed that how variational method can be used to find out this Z effective and the shielding constant. And the same problem we have done for the beryllium atom, where this average energy is given in the assignment, right? Z square minus 27Z, something like 7Z, something like that. So the same problem was done here, and we have found out that for using variational method, so with the correction of ceiling, it was find that 2.84, which was 2.91 in case of the second order perturbation correction, but in first order it was 2 point, minus 2.75. So there some improvement was there, but not as second order correction to the perturbation, right? And it was more or less close to that experimental value. So from here, what we understand that variational treatment is good, but we need something more than that, where we can play around with that. So here, before going that, he has shown that how ionization energy can be thought of a thing that this variational whatever energy we obtain using whatever ionization energy we obtain from a variational parameter and from a first order perturbation theory, it is actually large, because the gap was I think 1.5 electron volt, and for bond energy of a bond was which comparable to a energy of a bond. So we have to think of something more general thing. We can go to some Slater type orbitals, or he has discussed we can go to something Hilarious or
But this
in
Gaussian.
Hartree-Fock
Gaussian
limit,
type of.
this part also I didn't understand actually.
Yes. Which part?
Hartree-Fock limit.
Hartree-Fock limit means what I understand is that using these particular Slater type orbitals, we can go up to a certain limit. That is for suppose if we are taking a product of these
Okay.
Slater orbitals, then we are going to energy minimized of E is equal to 2.86
Okay.
arbitrary units and ionization energy of 23.4 electron volts. So that is a limit for these Slater type orbitals. Maybe now when we are using a different acha, so I think this is the best possible thing using a Slater type orbitals. We have let me go to another slide. There might be some more. You can get more thing. 51, 52, maybe this one. So in general, it was mentioned that Hartree-Fock and this cell consistent field is a computational thing, iterative method. So we'll because this Hartree-Fock operator or Hartree-Fock function itself will have this wave function in it. So we have to first.
Hartree-Fock is what? It's a person. It's an equation.
I think
It's
Harty, I
later an
read in
equation.
Levine's book, I read that Harty was someone who developed some equations, and
Mhm.
later I think Fock was someone I haven't read about Fock in specific name in the book,
Mm.
but I think he developed some numerical procedure to evaluate or to work with those equations or fields, something like that. That's why both their
No, my
names.
question is, variational theorem is already there.
Hmm,
Then you have Slater type orbitals are already there.
yes.
And the result that you get, why it is called Hartree-Fock limit, means what is their contribution?
With
Harty
two
and Fock
different.
took linear combinations of these letter type orbitals
Yes.
so
Okay.
that we can create any arbitrary function.
Hmm.
To I think
Uh,
it was done to reach the, I mean, to converge at the solution quickly.
hmm. And there
And
are a lot of
this
variational
was to
parameters. Not only suppose let me go to the another thing. You can see. Where is that? No, here it is not mentioned here. Let me go to that slide. See here. So what they have said that they have taken this particular some operator that mainly based on that radial thing, right?
Mhm.
So what they are saying that they have we have to guess such some wave function that phi of r and evaluate this effective potential energy and uh, using that variational parameter itself. But what we will see that this already has this phi term in it.
Mm.
So means this is becoming a computational parameters. Means you have to guess that thing and see if the energy is close or not. If not, then we have to do some improvement to our wave function. Then again check if this energy is close or not. It's like a iterative method.
But
Maybe this
isn't
is
that what we did in variational theorem also?
variational theorem. We also did something like that.
Theorem was the base theory, and now what we are doing is to implement the thing practically in real life
So
using
this is the
computer.
method you're
This
saying.
is the method. Yes. Means a try one kind of a trial wave function whose base is the method is based upon that variational method only.
Mhm.
Yeah. And now there will, in this case there will be much more variational parameters. There will be this coefficient as there is some linear combination, right? Again this
You need more
phi
computational power.
more we need more computational power. So that has been shown also that how many linear combination I think we can take. Let us see if that slide is there. I think that is not here. So maybe that using that Hartree-Fock limit, what they have reached to, I think, minus 2.8617 arbitrary unit. That is the Hartree-Fock limit they are saying.
Hmm.
So using that Hartree-Fock limit, they have reached to that, and using some different programs, not programs, means approximation method like that 13 order perturbation correction to the energy. By that, they have reached another 2.90 arbitrary unit, something like that.
Yeah.
So that is how that theory of this correlation energy or this thing has been obtained. Or because this, in this case also, that orbital approximation what we have taken for that one electron system also, something like a multi electron system also, that they are not correlated, or they don't they avoid each other. That thing we have established that time. But what is the correlation energy that has been calculated by that? So this is, so I also told you that I am also reading this, to be honest, the Hartree-Fock limit for the first time, Hartree-Fock theorem. So yes, so Hartree and Fock use this Slater orbitals and the theory of this variational method to get some more suitable or general wave functions. And okay, let us see what is the next lecture is there. Concluding remarks on Hartree-Fock. Okay, so this has been talked from, I think, McQueen. Yes. So now this, how this Hartree-Fock equation for a helium atom is only discussed. Yeah. See, Hartree-Fock equation from variational principle. So what they have choose that this is the our helium atom, and maybe these are our wave functions. We still don't know exactly what type of orbitals are these, or what wave functions are these. Fine. So the energy, average energy for this kind of trial wave function, they have tried to get that, and they have find this will be something like this. Now minimization of this energy with respect to phi, because phi is here, Hartree-Fock equation, that will be done, and that's all. That is we have discussed, and here also the spin part has been brought. Just a recapitulation. This is the Slater determinants, and this has been tried to show that the energy only have the term from the radial or the spatial part only, not from the spin part. So this has been discussed here, I guess. And from there, see, all these thing has been based on this variational method, right? That has been written here. Variational method, Fock operator. I think this Fock operator will have this kind of term again. This SCF, self consistent field thing, will again come up in. Okay, so they solved numerically by that consistent method. To be honest, I also didn't, if someone gives me literally numerical problems, I have to read much more. But I think we all get this idea that during variational theorem or perturbation theorem, what we are for perturbation theorem, what we are trying to do, that there are, we are trying to, if the perturbation is very small, then we are trying to think of an exactly solvable system, and from that, there we are trying to get the correction, or we are trying to use the perturbation thing. But when this then we introduce variational parameter, where variational theorem, where we find out that if we choose a trial wave function, maybe closely related to whatever we know, that if symmetry is there, something like that, from there we can choose an trial wave function, and from there we can get uh, a wave function that can have a energy, or have a average energy, which is equals to or more than the actual system, right? uh, and then also, if we don't know the actual system, and if we have some arbitrary or any general wave function. For that, we can go to that. That's why we need that is Hartree-Fock methods or something like that to get some use some more general wave functions. I think that is the gist. So, is it making sense, or you can, if you have anything to add, Avinash and Arunotpal?
No, nothing new to add. Actually,
Yes.
I have understood that much.
So it's
Also, one thing Sir was mentioning at a point, I think in this lecture or the previous lecture, like there is some software, but he didn't mention any software name. So,
hmm.
is there any specific software to do this kind of programs, or we can just from scratch build up using the usual numerical methods and numerical integration type programs to
There are some softwares. Generally, suppose you see some papers, right? Publications where they mention they have done Gaussian, or they have done some more thing like DFT, density functional theory calculation. I think there are some softwares, some packages are there, as you have seen that they have used some this kind of Gaussian or something like that, some
I think
basis level that has been.
most commonly used.
Yeah, Gaussian is a software that is been commonly used. So there are some softwares,
okay.
but there also you have to give your parameters or something like that. So you need to see this, I need to check that, something like that. So suppose uh, you have seen in like for our chemistry research problems, so what we try to generally do, I think Sir has already mentioned one, right? Sir has done one experiment 1 day or 2 day with a molecule, and to get a justification from the theory, that program ran for 1 year, something like that, in 1998 or in 2000 when Sir finished his PhD. I think some molecule, I think Sarah showed, right? Or maybe,
No, I
oh,
think
okay,
it
okay.
was not.
I think, I think it was not taught yet. I think in the next lecture, something like that, it might be discussed. So, it was something like that, a large molecule, not like helium or benzene. It is much more than that. More rings are there. As general organic molecules, organic dyes, suppose coumarin or something like that. So it has a large structure. So that can also be done. Means today people do that kind of theory. Means what is the ground state energy of that? So that can also be done. Suppose what is the bigger molecule you can think of right now? Suppose anthracene. And do you know, Arutpal, you have a different background, that's why I am asking. Do you know the structure of naphthalene, naphthalene or anthracene?
No.
Suppose, so let me tell you, you know the structure of benzene, right?
Yeah, yeah.
So if two benzene are fused, that is naphthalene, and if three benzene are fused on a single row, suppose, acha, let me draw it. I have, suppose here I am going to draw. You can see the screen, right?
Yeah.
Yes.
Suppose this is a benzene, right? Now this is a naphthalene. For naphthalene, like that, and another, if suppose another thing is there. This is anthracene. Am I drawing it correctly?
At the end,
And
just like the secondary.
yeah,
Yeah.
now it's fine, right? Yeah, now it's all aromatic. So like this is a bigger molecule than benzene. Of course, this is bigger than helium, right? So,
Yes.
so right now in physical chemistry or organic chemistry, we deal with larger molecules. For example, let me give one example of one molecule what we currently working in our lab, one dye. So I just want to give you the example how big one molecule can be. it will be much bigger than that, but we are currently working with this kind of molecule. We are not a, to be honest, a computational group. We are expert of this fluorescence spectroscopy and this spectroscopy related thing. And just give you one idea. So OCH3, this is the end of this one. So this molecule is known as DBMPT. It is just an abbreviation from a IUPAC name we have come up with. Anyway, so this kind of molecule we can actually do geometry optimized structure in gas phase, or in suppose in gas phase what will be its orientation, what will be the orientation of this molecule, or what will be its energy in the ground state, what will be its so that is the typical thing you can do, and much more thing you can do with time dependent DFT theory, something like that. We generally don't do it in our lab, but there are scientists or computational chemists who work on that. Sometimes we do it ourselves, or we try to collaborate with them. So we try to see that what will be the excited state, what will be the oscillator state, means what will be the absorption, theoretical absorption spectra, something like that. We can that can be understood from computation also. What will be suppose in uh, let me give you an idea that orientation I talked about, right? That how this benzene ring, is it in the same plane of this suppose this benzene, if it is same plane on this as this benzene, or this benzene, that angles, or what is the bond distance, optimum distance, that can be calculated from computations. So right now computation chemistry
That
has
need to have
evolved.
a crystal structure, right?
That can be also come from the crystal structure. That exactly, that is the means, final thing, that in crystal structure you will get all of those things. But suppose you are not getting the crystal structure,
Okay.
because not every for every molecule will get the crystals, right? Not everything will be crystalline. For this
Yes.
molecule we get the crystals and all the things. Means just for a example I'm telling. So
Mhm.
many more things can be achieved from computational chemistry. So when this computational thing will matched with this theory, will match your experiment, then will be in a some thing like, okay, so yes, so our experimental results are matching with the theoretical results. uh, so maybe we are close to what we are trying to, suppose we are getting some phenomena and we are trying to write that for particularly for this kind of orientation we are seeing this kind of fluorescence or something like that. So if we are getting say, this, what can we say, that similar observation from the theory itself, then
Hmm.
our
That explains. That gives you the.
that explanation is much more validated right
Hmm.
now, something like that. So yes, we can handle much more larger molecule also, and see how many heteroatoms are there. So there will be a lot of parameters are there. Lone pairs are there, something like that. But with current, so SAR said it took I think 1 year time to solve a similar kind of molecule, a large molecule SAR has discussed. In certain case, in generally in our lab we are trying to see this kind of interactions also. If uh, this if in ground state or in excited state, if there is any hydrogen bonding interaction is there, something like that, what will be the time take to this proton transfer, something like that we generally do in our lab. So that if that thing can be validated from the theory, it is good. We are
So you
trying we
do time dependent spectroscopy.
Experimentally,
Yeah.
yes. Experimentally, we do small computational thing. I am not an expert. I am not an expert. What can I say? I means I didn't do any computational thing in my life. So
Because for
we
my
have,
postdoc, I did
yeah.
some femtosecond chemistry in Taiwan.
Okay, okay, great. Yeah, so this you need lasers, all
Yeah.
kind of things for this
Mhm.
time dependent experiments, time resolved fluorescence studies, or even if the molecule is not fluorescence, you can use yeah, transient absorption spectra, something like that. But that is a whole together new avenue what I'm right now discussing. We are diluting the thing, but yes, with computational we can go to any larger molecule. So what I was discussing, that Sir said that during Sir's PhD's time that it took 1 years of time, because the maybe the software or the whatever the language was there, that was taking such more time processor. In today's time, it will take maybe a 3 hour or 1 day to solve this molecule. What is the geometry optimized structure? In 1 day only, for this the molecular what I am showing right now. So it has become day by day the researchers are doing different things. So whatever softwares are available right now, then those are also much more. Uh, they have some computational power so that we can do these studies. So this Hartifork, these things, just a basis of that thing, and based on that, this whole computational thing is dependent. And so whoever is interested in doing computational chemistry, they have to understand this Hartifork thing, and we also should understand. Means this is a baby step we have taken in this lecture just to get the idea. But if one is really want to do computational chemistry, then Hartifork is just the starting, as Sir also mentioned in one lecture, I guess, that
Yeah.
some computational chemist friend of him just said that Hartifork is just the beginning for their quantum.
Chemistry starts from Hartree.
Hartifork, and we are ending here only. Yeah. So today is almost 7. So what I suggest that, please, so tomorrow, so you already read the VBT part, right? Uh, so
Yeah.
do you have any specific doubt from VBT?
I haven't finished the lectures yet actually for week 10.
Okay. Okay, so you do that. I think for the MOT, I think the lecture series are also, I think, out, right? Week 11.
Yeah, it is out.
Yes.
Yes. So you also try to finish that part. Why I am saying that? Because I will be sending that tutorial problem what I was saying. So that is based on that VBT and MOT, mainly based on MOT, molecular orbital theory. We'll just solve that, or maybe discuss that part in tomorrow's, not tomorrow, next live session, or maybe on that final live session. With that, we can finish here, and I think Arunotpal is ready to go to the puja pandals. Uh,
No, actually, I am staying at home today. I have one doubt
yes, okay, okay,
regarding a problem from Griffith. I mean, I solved the problem and everything mathematically. I have the
okay,
doubt regarding the interpretation.
okay.
Like they gave us a wave function like psi x is equal to 3 psi 0 x plus 4 psi 1 x.
Acha, let me write that.
Okay.
Let me see if we can solve it. Yeah, tell me.
Yeah, psi x
Psi A,
is equal to 3 psi 0 x.
psi 0 or
Yeah,
zeroth.
0 0. I mean subscript
Acha,
0
okay.
plus 4 psi 1 x.
Psi 1, okay.
So psi 0 and psi 1
I
are
mean,
the
psi is in
wave,
capital maybe.
wave functions for harmonic oscillator, quantum harmonic oscillator.
Yes, v is equal to 0 and v is equal to 1.
Yeah, and so they asked like normalize it and find the whole time dependent solution, and then then find the average of position, momentum, and Hamiltonian. I have done all that. So if we normalize, we would get 1/5 multiplied with both the terms.
Okay, and psi 0x and psi 1x is just a harmonic oscillator solution, or that has been we don't really need to solve that, right? Because we can take a normalization constant n and do that thing, right?
Yeah, like I did that like that
Okay, okay.
also. So my question is, when we are calculating the Hamiltonian,
Hmm.
so we would get 3/5 square plus 4/5 square.
Hmm.
So in practically, when like we are applying Hamiltonian operator on
Wait, so
this
what will be the normalization constant here? Let me check.
one by
Uh,
five,
1 by 5 you are saying. Okay, so that is because n square is n square 3 square sin 0 square x star is that, and plus n square 4 square, and the rest of the terms are orthogonal to each other.
yes,
That is 1. So n square is what will be the 1? It is 1. That is
this is also one.
also 1.
So
So
we get 1
1
by
by
25.
25. So n is plus minus 1 by 5, or we can take any one of that. So you are taking n is equal to 1 by 5. So this is the
Yeah,
normalization. Okay. Okay. So capital psi of x is equal to 3 by 5 psi naught x plus 4 by 5 psi 1. Okay.
psi 1 of x.
Uh, now,
Now they asked us to calculate the Hamiltonian's, I mean average of Hamiltonian, expectation of Hamiltonian.
that is the expectation energy, right? Means
Average energy.
average energy, or the expectation value of energy, right?
Yeah,
So that will be, and right now it is normalized, so it will be capital psi of x, it will be h
H.
of that, and there is psi of x, and this is a linear combination. So this part you will replace like here, right? Yes.
yeah.
So this will be the average energy or something. Yes. Now, so this will
So
only be possible when you you have these values of psi of x and psi of energy of this thing. So that we already know, right? Is it something like that? This is half h for us is right. Not h cut, but h nu. Okay. And
okay.
is it means I'm saying if it is given, or we have to
No,
take
nothing
some.
is given.
Okay, so just it
So
is
I
given, then
actually calculated, yeah, just given that psi 0 and psi 1 are from the quantum harmonic oscillator, and we have such a wave function psi that it is in that way.
okay, okay. So so how did you calculate the average energy
So
then?
I calculated like I like this way that psi is expressed as a linear combination of two basis functions.
Yes.
So I took C mod C1 square plus mod C2, sorry, not C1, C0 square plus mod C1 square in that sense.
Hmm. Hmm. That is your average energy.
No, I mean mod C0 square into E0 plus mod C1 square into E1. In that way, I calculated.
Okay. And then how much did you get?
I got 57 by 50.
So you got 3 by 5 mod square energy of E0
Yeah,
plus
plus
4 by
4
5.
by 5 mod square E1.
uh, okay.
So I
And
got it would come like 1.14 h cut omega.
so so that is you took again half h nu, right? What we I
Yeah,
just
yeah,
said.
yeah.
Yes. So I think we are also going to get the same thing from here, right? Because 3 by psi 0, right? And I'm not writing that
Yes, if you write, it would be the same.
same
Like
thing, right?
before, there was another problem with just psi 0 plus psi 1. I
Yes.
did this whole thing.
Yeah, you just
Uh,
step jump one. Yeah, we can do that. That is actually good. Yeah. Yes.
So, like my
So,
question here is like when we are applying an operator to an wave function, then
huh.
we determine that observable's value, right?
Yes.
So when we measure the energy of total energy of that psi function, do we get this average value or we get energy of only one of those states?
You get the
Right now
average.
right now you have performed the average energy. So suppose
Okay.
if you measure the energy once, suppose you are having the Hamiltonian working on the capital psi, and this capital psi is this one. Okay. So
Yeah.
when we will perform once, we will get only one of the energies. One of the means either energy of psi 0 or either the energy of psi 1. So you don't know which. So that again goes to that entanglement theory, means before measurement you don't
Yeah.
know what you are going to get. Just after doing the measurement you will get either from psi 0 or the energy of psi 1.
Okay. So when
And
we are measuring only one wave for only one wave function, we are getting the energy, and rest of the wave functions are collapsing.
yes, means collapsing to that particular, suppose it will if you are measuring one, so you will maybe getting the energy for E0. So when you will get the energy E0, when it will be collapsed to psi 0. So if it
Yes.
collapsed to psi 1, then you will get the energy E1.
E1.
So so if you do a this measurement multiple times, you will get different values. E0 E1, E0 E1, or E0, something like that. Okay.
Yeah.
So before doing the measurement, you don't know. So that is the collapse of a wave function, and that is the entanglement thing. That it is entangled before doing the measurement, and after the measurement you will get on that. And this average value means this is the average of all these things. Suppose from one measurements you are getting E0. Okay. Second, you do second time you are doing, you again get E0. Third time again you do E0. Nine, to do a 1 lakh time you get this many time of E0. N time E0, M time, sorry, M time E1. So now your average will be N into E0 plus M into E1 by N plus M number of measurements, and that is actually this thing,
Okay.
this average energy. And that's because when you do a large number of measurements, then the probability is the square of these coefficients, right?
Yeah.
That
C0
is, you
square
will
or something.
find E0 3 by 5 3 9 9 by 25 times.
Yeah. That was
uh,
also the question actually, like find the probability of getting E0 and E1.
yes, so this is the question we have discussed on the first tutorial problem. I think you will remember that,
Yeah.
tutorial 1 maybe. Yes, I hope now the thing is clear, the
Yeah.
physical meaning.
Yeah. Yeah.
Okay.
And when we express any arbitrary for a
Hmm.
given model, suppose simple harmonic oscillator model, in terms of all the known functions like psi0, psi1, those are orthogonal, orthonormal to each other.
Hmm.
So we are doing that to get these probabilities easily, right?
I
To
didn't
calculate.
get your question. Can you
I
repeat?
mean, suppose we are taking any arbitrary psi, suppose a triangular kind of function.
Okay.
So it will be normalizable and a valid wave function.
Hmm.
And now we are expressing that psi as a linear combination of all the psi0, psi1 to up to psi n.
Okay.
Uh, so we are doing this so that we can have a good theoretical understanding of getting any a probability of those energies or average energies like that.
No, actually, see this capital psi x is equal to this 3 psi 0 x or psi 1 x. Suppose this is not for a Hamilton harmonic oscillator, but for a uh, uh, particularly in a 1D box or systems we have solved yet, right? For a hydrogen atom. So
Yeah.
it is like that our suppose in a particle in a box, or for a hydrogen atom, that our energies are uh, suppose this is the energy axis, right? So this is n is equal to 1, this is n equals to 2, this is for a particle in a box, that's why n is equal to 1 is the ground state. Now this is something like that our whole wave function, our whole means the capital psi here can be written as a means linear combination of this wave function as well as this and whatever other wave function
Wave
is there.
functions are there.
Like that we are writing here. So for this case, suppose our harmonic oscillator something is like that. So our two energies are there. So this is mu v equals to 0, this is v equals to 1. So our given wave function is something like a linear combination of C1 psi 0 plus C2 psi 1. So this is we are not really writing it from a for a given equation. We are writing it something from assumption, right? That given that psi is such, but suppose we are finding one system or one wave function C1 psi 1 plus C2 psi 2. That means that we have a wave function in such a way where two of the states are entangled. Two of the states means two energy states are there, and that is entangled in such a way that C1 psi 1 and C2 psi 2. That can be a one possibility. I hope I don't know I did I gave you the answer or did I derail from that?
This question came to my mind like in Griffith's book, like they have shown that how to calculate C1, C2, and there are lots of problems actually, almost 4 to 5 problems based on this, like
Hmm.
expressing an arbitrary psi as a linear combination of those basis functions or vectors.
Hmm.
So that's why I was wondering, like, when do we need to do this?
So we are not doing it from a particular purpose, but the system is like that. Means our psi is given like that. Means the psi has the terms from its components, different energy states. So
Okay.
means we don't really know that where our molecule is current. Suppose our particle is in ground state or in n equals to 2 or n equals to 3, we don't know
With
from these two.
probability of both these states.
Yes, yes. So then we are saying that the psi 3 doesn't have any contribution or something like that. Any other doubts
No,
or no?
I have solved up to chapter 3, and others I have managed to solve them.
Okay. Okay. Okay then. So we'll meet on next day. So let us stop our meeting for today, and I will share these notes with you.